Today we're going to talk about several topics that you will need to have refreshed for this course in organic chem. So without spending a lot more time, let's talk about them as they occur. First one is Lewis structures. The difference between Lewis structures in organic and Lewis structures in regular chem is organic focuses mainly on carbon, hydrogen, nitrogen, oxygen, and fluorine. And carbon and hydrogen are always in it. In inorganic, you get different chemicals like F6 or CO. Only in organic, these are the main focus. Now let's talk about the rules. These rules are similar to what you learned in Chem 1 with some minor modifications. So let's go through it. First rule, you cannot have more than 8 electrons or 4 bonds attached to carbon. Okay? We still have to have 8 electrons around every atom, but for nitrogen we just need 3 bonds, 2 for oxygen and 1 for hydrogen. What this means in nitrogen, you will have 3 bonds attached to it and a 4th, because you also need the octet of unpaired electrons, 2 unpaired electrons. Next, use a dash to represent the bonds and dots to represent unpaired electrons. Depending on how your instructor taught you in Chem 1, some only did dots, some did bonds, but this is the combination that we will need to do for organic. Next, a refresh. Each single bond contains 2 electrons. That's a double bond, which contains 4 electrons. 3 dashes is a triple bond, which contains 6. The next item, again similar to Chem 1, the number of valence electrons of the specified molecule must equal the number of electrons calculated from the formula provided. Otherwise, it will not be a correct structure. Now, what's different in organic, and we'll see what our examples is, you can have more than one structure for the same molecular formula. And item 5, and another special item related to organic. You need to also make sure when you're doing your organic review of the structure that the carbons and hydrogens and oxygens or whatever else in there and the proposed final structure matches up with the original formula. You can have a situation where, again, if you do not do it right, you could have more hydrogens than you needed, less hydrogens because you missed or added a double bond or a triple bond. Next thing we're going to talk about is some examples. Now let's take an organic molecule, C3H8O. First thing we do is calculate the number of valence electrons associated with it. Carbon has 4, so that's 3 times 4 is 12. Hydrogen has 8, that makes it 20. And oxygen has 6, so that's how we get to 26. So the first step we want to do, which is very similar to what we did in inorganic, is to draw a skeleton structure. The difference in organic is you're going to have a lot of carbons. And as you can tell from just looking at this one example, we'll call this carbon 1, carbon 2, carbon 3. In this case, oxygen is connected to carbon 3. Let's go over here on the right side. Carbon 1, carbon 2, carbon 3. In this case, oxygen is connected to carbon 2. So we have at least two possible structures. A lot of times in organic, you'll have multiple structures. Your instructor will get into what these are called. Typically they're called constitutional isomers, but the instructor will get into how one determines how to handle that. What I want to do here today is just give you an example of how you would use Lewis structure notation. So the first step is we have done the skeleton. Next step is, remember, every atom has to have 8 electrons. And because of organic's unique nature, there's a specificity associated with certain atoms. Carbon needs 4 bonds. Oxygen needs 2. Nitrogen needs 3. The rest are usually filled in with unpaired electrons. So let's look at this structure. And remember, all the major atoms must have 8, with the exception of hydrogen, because hydrogen is happy with 2. So let's talk about this one right now. Okay? Again, remember, every bond is 2 electrons. So we have just filled this up so that we have 4 bonds around this carbon, 4 bonds around this carbon, 4 bonds around this carbon. We also looked at the oxygen. We added a hydrogen because what else can we add to it that makes any sense? And that's how we get this. You can have situations, and we'll show it the next one, where you can have oxygen connected between the carbons. In this case, we're just going to do it on the peripheral. So this is how this structure looks like. Let's go over here. Another proposed structure. 4 here, and we have 3 here, so we have to add a 4th that I didn't add. Now that is legit. Okay, over here, again 4, and the oxygen needs a hydrogen. Now, the final step. Final step, we calculate from the structure how many valence electrons. We also count the number of carbons and the number of hydrogens. So let's look at this. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So it satisfies that first criteria. Now let's count the number of carbons. Obviously there's 3. Obviously there's 1 oxygen. So far so good. Now the critical one, the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. That is an acceptable structure. Let's now go over to this one. Same drill. We know that the number of carbons matches up, number of oxygens match up, and I'm going to take a little bit of a shortcut. How about the number of hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. High probability that if the structures match up this well, the number of valence electrons will equal. So let's just confirm. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. These are both valid structures, but they are different from a Lewis structure standpoint, and your instructor will get into more detail about the differences. Next topic, we're going to talk about formal charges. And you're going to ask, why are we worried about formal charges? You're going to find, especially for your first test, that the only way to determine equivalent resonance structures is to know your formal charges, because you will see, once your instructor goes over resonance structures in organic, which are totally different than the resonance structures you were taught in Chem 1. So it's important that you understand formal charges and how to calculate them. So first rule, calculation. FC stands for formal charge. Is the number of valence electrons of the individual atoms. Remember, we're talking about individual atoms. How do you get the valence electrons? Look at the periodic table. If it's in group 4, 4, group 5, 5, group 6, 6, group 7, 7. And you subtract from that the number of bonds attached to that specific atom, and also the number of unpaired electrons associated with that specific atom. The next rule is that the total number of formal charges of all the atoms in a molecule must equal the charges of the molecule. What does that mean? If the molecule is neutral, the sum total of the charges must equal 0. The molecule has a charge, the sum total of the charges must equal the charge of the molecule. So let's look at the current examples. This one is the ammonium ion, NH plus 4. First thing you do is draw the Lewis structure. Again, I had said in a previous one that you can't have 4 bonds attached to nitrogen. That was in what I would call a structured molecule. Separately, we can do that right now. Okay, so you look at this, and now we've satisfied the 8. Because now let's calculate the formal charge of nitrogen. The reason I'm not doing hydrogen, because it's self-evident when you do hydrogen that the charges on that are going to be pretty much equal out. So let's do the formal charge of nitrogen. Formal charge of the nitrogen is going to be The number of valence electrons is 5 minus the number of bonds plus the number of unpaired electrons, which gives us a +1, which is equal to this. Now let's talk about CO. Here's the Lewis structure. Okay, now let's look at the individual atoms associated with the Lewis structure. Let's do the formal charge on carbon. Formal charge of carbon is 4, the number of valence electrons, minus the number of bonds, which is a triple bond, plus the number of unpaired electrons. When you do that, you get a total of -1. Now you do the same thing for oxygen. 6, which is from the periodic table, minus 3 bonds, plus 2 unpaired electrons. And when you do that, you get +1. Now we take -1 plus 1. What's the sum total of charge? 0. What's the charge here? 0. That is how you do formal charges. In this section, we're going to talk about hybrid orbitals and how they apply to organic. Remembering that the hybrid orbitals we learned from in Chem 1 do apply to organic, but they apply in a little bit of a different configuration. But before we go and discuss how it applies to organic, we're going to go back and look at some definitions. First definition is a non-bonding domain. What is that? Fancy word for unpaired electrons on individual atoms. Now remember, to do these we have to have Lewis structures. Bonding domains, an area in which electrons are shared between atoms. So let's go back and look what that means. And a single bond, or a double bond, or a triple bond is classified as one bonding domain. So when we're looking at identifying a hybrid orbital as sp, that means 2 bonding domains, or possibly 1 bonding domain and 1 non-bonding domain. Practically, that will not happen. sp2 is 3 bonding domains. sp3 is 4 bonding domains based on these definitions. So best way to learn is to go by examples. So let's look at a couple examples. This is carbon 1. Carbon 1 has 2 bonding domains. So carbon 1 is going to be an sp because it has 2. Carbon 2, again, 1 triple bond and 1 single bond. It is also going to be sp. Now let's go to the next structure. Again, carbon 1. Carbon 1 here has 3 bonding domains, 2 single bonds and 1 double bond. Therefore, it's going to be 3 and it'll be an sp2. Since this is symmetrical, you're going to get the same answer for carbon 2. Now let's go to the next structure. This structure has 3 single bonds and 1 unpaired. Okay, what does that mean? Total of 4, because we have 3 bonding domains and 1 non-bonding domain, so this makes this an sp3. You notice 2, 3, 4. Similar with this one. Carbon has 4 individual bonds, so it will be an sp3. Now let's try this one. We're looking at carbon. How many bonds? A double bond on one side, double bond on another side. So that is a total of 2 bonding domains, so that will be sp. Now let's apply the same thought processes to an organic. The difference between organic and inorganic is the organic molecules are going to be longer, be more complex. For this exercise, we're going to take something that's reasonably straightforward, this structure right here. In this structure right here, there are 4 carbons that we've identified that we want to get the bonding domains. There's more than 4, but in this case, the only ones we've identified. This one, this one, this one, and this one. Okay, so let's look at this one. This carbon 1 has 2 single bonds because it's attached to the hydrogen and 1 double bond. Therefore, it's going to be an sp2. This carbon 2 has the single bonds attached differently and a double bond. So that is also going to be an sp2. Now let's look at this carbon 3. Has a single bond and a triple bond. That's going to be sp. Carbon 4 is going to be a single bond to connect to the H and a triple bond. That is effectively how you apply the hybrid orbitals to the practical application. Your instructor may get into more theory of how it works, but for this exercise, we just want to show you how to apply it. Thank you. In this section, we're going to show the difference in the similarities between Lewis structures and line structures on an uncharged molecule. it is important that everybody becomes very familiar with line structures, as they will be the main mechanism by which you will be looking at organic molecules in organic 1 and 2. So without much further ado, let's talk a little bit about line structures. What makes them different from Lewis structures? First of all, in a line structure, you do not identify the carbons or the hydrogens associated with those specific carbons. Second thing, we'll always identify atoms other than carbon with their respective bonded hydrogens. So if it's nitrogen, their respective bonded hydrogens will be attached to it. Remember, uncharged carbon, nitrogen, oxygen want 4 bonds, 3 bonds, and 2 bonds to be happy. That makes it a little easier for you to see the line structure. The final statement, line structures will often be shown at an angle with each other rather than a straight line. And some students ask why, and I'm going to explain it very shortly. So let's take the first structure. This structure right here has 1, 2, 3, 4, 5 carbons. And if you notice, in the Lewis structure, this carbon has these 2 carbons attached to it. Then it has a hydrogen associated with this. Then next to it is the carbon here. Now, why do we know that? Because it's 2 hydrogens, so it's got to be this way. Also here. Then nitrogen. Again, nitrogen is happy with 3. Carbon is happy with 4. So you can see that is satisfied. Now, let's see how it looks like in a line structure. The line structure here, a proposed line structure for here, would have this atom, which is this one, here. This atom, which is this one, here. This atom, here. Obviously you can put it in different directions, but you'll find out why it makes sense to do it this way. Then we angle up for this one, angle down for this one, and then we go right across here for the nitrogen. Again, line structures are useful from a standpoint of spatial space that it saves, and takes less time if you had to draw all this and less paper. Now some people say, well, why can't they be horizontal and vertical? Well, here's an example. It really gets difficult to sort out which ones, where the carbons are, etc., when you do it this way. Much easier when you have it at an angle with each other. So that's one of the reasons why when you look at the line structures, almost all of them are going to have some kind of an angle relationship. It looks like a 45. Most of them seem to be that way. But I don't think the 45 is the angle that's specified. It's just an angle that makes sense. It could be 60, 30. Now, let's talk about another structure. Here we are, CH3, right over here. Okay, again, how many carbons in this structure? 4. Okay? Because it's CH3, we know this is this. 2 CH2s right here. We have a carbon, and this is the only bonding structure that we have that will satisfy the fact that we will have 4 here, 4 bonds for carbon, and we also will have oxygen and hydrogen. If you notice, I didn't put the dots here. The dots are supposed to be here. I just wanted to show you how the structure sometimes, because in a test, your instructor may take off. These dots are a little faded, but they are there. But that's should have two sets of dots here. Okay? Okay, so now let's do the corresponding line structure. This is this, this is this, this is this, this is this one. And I recommend for students to get familiar with line structures, have a colored pencil that is erasable so you can put a dot here so you can make sure you don't make the mistake that a lot of students make. They overcount or undercount the carbons. Again, for purposes of our exercise, these are supposed to have dots. Some instructors take off, some don't, but technically you should have dots because oxygen needs to have 8. So now that I've shown you when it's wrong, let me add it and show you when it's right. Now this is the correct line structure and a correct Lewis structure. And again, it takes a while to get used to it. My advice to students is, if you're a little dyslexic, the colored pencils, the erasable pencils work. Putting them at an angle and remembering. One of the things I tell people until they get comfortable with line structures is draw the hydrogens in. When I say draw the hydrogens in, yes, they can't be part of your final structure, but if you're not sure, you know you have to have 3 here, 2 here, 2 here. And that just gives you a feel for having the right number of hydrogens over here. This is incorrect, but this is a tool you can use if you're not sure how many bonds are associated with this carbon, to make yourself more comfortable. Best example for line structures is just do several of them and you'll get a feel for it. It's critical that you understand them, because the foundation of the future lectures that your instructor is going to be giving you will be based on line structures. They will be getting away from those structures as quickly as possible for all the reasons we talked about. Okay, today we're going to talk about conjugate acids and bases, is how they apply to organic. But before we do that, we need to talk about what it means from 1046. So, a couple of definitions. First, a conjugate acid is one more hydrogen than its base. Conjugate base is one less hydrogen than its acid. Oh, that sounds real good, but let's look at examples. Examples always make it easier for you to understand. So here's an acid, here's its base. What's the difference? I ripped off one hydrogen, and now when I ripped off the hydrogen, which is a positive charge, I have one less, and therefore the charge becomes minus. Here we have H3O plus, the hydronium atom. Again, I rip off one hydrogen, we also lose a charge, and that becomes H2O. If I did the reverse, if I said I wanted the conjugate acid of this, I'd be adding a hydrogen. Therefore, I'd be adding a charge. Same thing here. I'd be adding a hydrogen, and the charge would go away. That's pretty straightforward for inorganic. But for organic, it's even easier, because the structures are going to be very similar. In other words, whatever you have here, you're going to have something similar on the other side. So let's talk about a couple of organic problems. In this problem, and we all know these reactions are acid-base, acid-base. So we have an acid, we're going to have a base, and vice versa. So let's talk about this. We're trying to find what X is and what Y is. All right? Well, we know from looking at this that this is probably going to be X, because there's no way this is going to look like this. So what's it going to be? Well, the most common sensible thing would be to add an H, because it becomes its conjugate acid. So if this is the acid, then we know this is the base, so this is going to have to be the acid, so it means we're going to add a hydrogen. And we get water, and we get that, so that's a pretty easy way of doing it. Now let's have another example. Same idea. We're trying to find X, we're trying to find Y. Again, let's look at this. NH2. We know that nitrogen wants 3 to be happy. So there's no way we're going to add a fourth, but we could take one away. If we take one away, that makes this the conjugate base, which makes this the conjugate acid. Okay, which makes this going to be the conjugate base, which is going to be one less hydrogen. So when we do this, we end up with this for X and this for Y. It's that straightforward and organic. Just pick one, you know it's acid base, and the other one will just flow through it. Thank you.